Because I would say on this side, I have molecules hitting over here, and this is actually bigger than this. So this would be way more than 185. But I would have 185 on this side also. And so if you take these two sides, you know, it's easy for us to forget about these mighty midgets until you take them away on one side, and then you can have the effect of them. And this little rubber square is nice because when you place it on a flat surface and kind of hard like this, that chases and forces them all out of the way on the side between the rubber and the whiteboard. And so if I try to pull it off, whoops, if I pull it here, I can't. And the reason I can't pull it off is the molecules in this room are pushing in and I don't have any pushing back. And so I would have to pull with my hand more than 185 in order to take it off. Or I could let some molecules in. And so if I just lift this corner up, I can let the molecules in the other side and do the pushing. So stuck, free. Stuck, free. And take advantage of these mighty midgets. And maybe you've done that. I see a lot of those, what do they call those, sucker things that you can stick on like the tile in your bathroom. I know I have one for a couple of them for my kids there in the shower. It's just this little sucky thing. You just go right onto the tile and it sticks there, and they can then hang their washcloths on it here. And so it just sticks there. And it's really stuck there because of the air pressure on the outside. It's not the vacuum on the inside, but it's the pressure of the molecules, what I call the mighty midgets, on the outside. Well, I better keep going here because time's getting away from me here, and there's lots to talk about in this chapter here. So let's keep talking. But if you recall, a little while ago, I had here on the board 3 terms that I were trying to convey to you. The first one was the symbol V for the volume. The second one was capital P for the pressure, and that's what I've spent this last 20 minutes or so talking about here, is what is pressure, what are the units, and trying to give you an idea, and maybe even a surprising idea that even though we can't see these little tiny things, they're going very fast, and there's lots of them, and the result of that is significant. And of course, the other one I'm trying to say here is the idea of temperature. And maybe I'll do this one a little bit quicker, but I'll come back over here. I'll just adjust this one so that the BBs are moving at a much slower rate. And I want you then to kind of picture this with the BBs moving slow compared to the BBs moving fast. So that's fast. And that's slow. And that's what temperature is. You see, when you say something is hot, you, of course, usually say, well, it's hot because I put my hand on it and I can feel that it's hot. And if it's hot enough, it could actually burn me. But what you're actually feeling is the molecules moving faster and faster. And so this is our ideal gas model. It's what is referred to as the kinetic theory, when the early scientists were like, wait a minute, what is the difference between something that is cold and something that is fast? And they came up after a lot of thinking and discussing that the world is really made of these little tiny atoms, and they bounce around. And as they move faster, as the temperature goes up, they move faster. And so for the first time in really history, we begin to understand what is really going on a molecular level, on a microscopic level, between something hot and something cold. And so it's these 3 ideas, and I didn't say much about volume, I think you know about volume, but it's pressure and temperature that I really wanted you to get a good handle on. And so I spent a lot of time with pressure. I'll just show you temperature one more time here, but again, you can kind of see that. If this is low temperature, they're barely moving. And if I warm it up, if you will, they move really fast. And so the mental picture I want you to have is an idea about temperature. Temperature is that kinetic motion. Remember, we really even had this discussion already when we did conservation of energy back in Chapter 7. Back in Chapter 7, if you remember, I was dropping a 1 kilogram mass from here, and as I dropped the 1 kilogram mass and as it fell, I would say things like, okay, what is the total energy? And if you remember, it was 10 joules up here. And as it fell, I tried to emphasize it always remains as 10 joules. And so as it went down, it lost gravitational potential energy, but it gained kinetic energy. And even when it hit the ground and rolled to a stop, it still had 10 joules of energy. Those 10 joules of energy, though, were not kinetic because it came to a stop. And they were not gravitational potential because it fell all the way to the ground. Well, where were they? And this is the answer. They were maybe moving slowly like this when the molecules were up here at the top. And then when they hit, the impact made these molecules and these molecules go fast. And so it would look something like this, but then they would go really fast. And that's where that energy is. So we didn't lose the energy. We just was hard to see because it was now in a kinetic energy of the molecules. And that's when I had brought this little machine out before, so you can get an idea. And so if I didn't get that idea across to you in the past, let me repeat it now. That's what temperature is. Something that is hot means that the molecules are going faster and faster. And something that is cold means the molecules or the atoms are going slower and slower. And so that's the three big things about this ideal gas model. And so when you look at these molecules, hopefully you'll see these molecules bouncing around and you'll recognize their volume. You'll recognize their pressure comes from the impact, and the impact would, of course, be how many and how fast and what mass do they have. And then the temperature is really telling you how much kinetic energy do they have. And that's the big picture. In fact, I thought this would be a good time to show you a couple of little experiments that gave scientists, well, I'll leave this up here, the first clue that this kinetic theory, or the clue to the kinetic theory, that materials were actually made out of little tiny things, which we call atoms, and that they jiggle around. And when you warm them up, they jiggle faster. And when you cool them down, they jiggle slower. Because watch this. Not only did you see them going faster, I think you saw something else. Let me try it again here. I'll start with them going slow. Okay. So here they are going slow. And then I warm it up. Okay. So let me give them more kinetic energy. There they go. Now I'm hoping on video, besides sounding louder, you can actually see that they are moving faster. But did you also see something else? Did you also see that the styrofoam went up higher that was trapping them? You see that when they start bouncing around faster and they are hitting each other a little harder, they ricochet more and they lift up. That is, they expand their space. And it's that expansion of the space that was this beginning clue to the early scientists that temperature really is a motion of some microscopic things that we can't see with our eyes. And as they bounce around, they just go faster and faster and faster, and so they'll need more space. And so your author uses this as an opportunity to say that there is this fundamental idea, as we talk about temperature, of what we call thermal expansion. That is, when you make something hotter, the atoms move faster. As they move faster, they will need more space. They will need a bigger volume. And that's referred to as thermal expansion. And let me just show you a couple of those as we're talking along here. Let me kind of move this out of the way so that I don't damage it, because I have up here this brass rod. Now, this brass rod sits on this little device that has a needle that I'm hoping you can kind of see on the video, that as the rod moves back and forth, the needle spins. And the needle spins a lot. And so this little instrument over here with this brass rod is really a little instrument that's saying how much did the brass rod move. I can move it back and forth, back and forth. And that needle will spin. And so how much that needle spins is an indication of how much did it move. Because here's kind of the fun experiment here. I'm going to take this little, I'll call it a stopper on this end. But it's got a little edge that kind of holds the end of this brass rod. So that if I move the brass rod, it does not move in relationship to this end of the rod, which I guess would be the right end. The only side that can move is the left side, and that's hooked to the needle. In fact, it's kind of nice to put a little extra weight on the brass rod. It just gives it a little bit of tension. Because again, if I just kind of move it back and forth, you can see the needle spin. And like I said, the needle moves quite a bit for just the small movement of my hand over here. So let me do this. Let me start with the needle straight up. And then let me take the propane torch here. And what do you think will happen if I then warm this brass rod? And so as I warm the brass rod, I'm hoping you'll see that the needle starts moving. That's telling me that the brass rod is actually getting bigger. It's expanding. Now, not by much. That's why I've got this fancy little equipment. I can't see it with my eyes. It's not that much. But it is enough that right now the needle has moved a quarter of a circle. And so this is what we refer to as thermal expansion. This was the early experiment by the early scientists that said, you know, why does it get bigger? And they finally begin to realize this is just the equivalent of a bunch of bouncing BBs, that they're just kind of bouncing around. In fact, as I talk for the next few moments, let's keep coming back and looking at it. But now this brass rod will cool down. And as it cools down, you will see it shrink. And that is, you will see this needle going back. And you can see it's already come back a little bit. It's got a long way to go still, because it's a little bit under a quarter, but it was a little bit more than over a quarter when I first turned off my propane torch. And so now it is coming back further and further. And so while that cools down, let me come over here and kind of show you another one that's kind of fun to see, and maybe even a little bit of a surprise. I'll come over here and get another torch going here. And so let me take my burner here. Get a little more gas so it gets nice and hot. But to illustrate this thermal expansion, again, I have a ring and a sphere. Now, the diameter of this sphere is actually the same as the inner diameter of the ring. It just barely fits through. And to illustrate thermal expansion then, let me put the sphere in the hot flame, but not the ring. And so as I place it in here, and the sphere takes a little while to get the whole thing good and hot because it's, a solid piece of metal. So I need to leave it here for a little while. So I'll keep talking. In fact, while I'm getting it warm, maybe it's a good time to jump back and see that needle. Oh yeah, see, look, the needle has gone way back now. It's still got a ways to go though. All right, well, back to this. Now I think it's warm enough, so I'll give it a try here. And so now that I've warmed this up, watch what happens as I try to put the sphere through the ring. Yep, see? I'm making an effort here. I'm not playing around. I can't push it through here. Let me keep it warm. And so this sphere does get bigger. That's what I mean by the thermal expansion. In fact, let me turn on a little cool water here and use that to cool down the sphere. And so once it cools down, it should slow down the molecules. It should go back to its original size, and sure enough, it fits. Now let me show you a second one that I think is a little bit of a surprise. I'm going to have to re-warm the sphere. And so give me a minute for that. I don't think it's enough. Oh. I'll go a little bit more because it didn't quite fit in, so maybe it's enough to illustrate it. But I want to illustrate, if I do this, it doesn't fit. But here's always a fun one to ask. What about a ring? What happens if you warm a ring? Now I'll leave the sphere in the flame, so it'll stay big. But I think what surprises students is this experiment. I want to talk about it. But the inside of the ring actually gets bigger, not smaller, bigger. Oh, watch, I'll illustrate that. Now that they're both in the fire, look at that. It does fit through. Hopefully I'll even prove it to you. I'll leave the sphere hot, and let me cool down the ring. So as I cool down the ring, leaving the sphere hot, you'll see it doesn't fit. And of course, if I cool down both of them, it'll now fit. And so the size does change with the temperature. And again, the reason for that is right back here. It's what we call the kinetic theory. Now, my focus is on gases, and right now I'm showing you with solids. But the solids are the same thing, that they're made out of a bunch of atoms. And if you make them hotter, the molecules go faster. And as they go faster, they bounce into each other a little harder, and they need more space. And I'm curious on this one here. We're almost cooled all the way down. We're almost back to the same size, and it's almost straight up for the needle. And in fact, let me show you another one, and then I'll explain why the opening in the ring actually got bigger, because I think that's a surprising one. But here's another fun one to see, which again, I'll explain in more detail after I show this and draw some pictures. But this is a neat one because from your distance, it may look like this is one piece of metal, but it is not. It has brass on this side and stainless steel on the other side. And the two pieces of metal are hooked together, welded together, and they're the same length. But watch what happens when I put them into a flame. And I hope what you're seeing here is the metal piece curved. We call this a bi-piece of metal, a bimetal. And it's a bimetal, of course, because it's made out of two pieces, in this case, stainless steel and brass. But as I'm talking to you now, can you see it's beginning to straighten up? In fact, let me cool it down a little bit faster. And see, it's a little straighter. Get a little bit of cool water going, Maybe not too much here. I'll cool it down. And when I cool it down, it's back to being straight again. Why? All right, well, let's talk with the ring first. And so if I were to come over here and draw a picture of a ring, it might look something like this. Here is the inner radius, and here is the outer radius, and in my case, then there's a little handle down here. And the metal ring, of course, is made out of atoms, and of course, in this case, it's a brass, so it's made out of mostly copper atoms. So I'll just say I've copper atoms. And so these copper atoms are bouncing around. And when I heat them up, they get bigger. That's the part I'm trying to show you. That is this part about thermal expansion. This is the part about the whole idea of the atomic structure and temperature that is covered in this chapter, that if you make something hotter, they go faster. And I think most people stop short of the full problem. They do this. They said, oh, okay, well, if you heat it up, doesn't that mean that the metal will expand like this? It'll expand inward and it will expand outward. And although that's true, if you stop there, you're going to think that the hole in the ring gets smaller, because there's also this going on. They bounce and make the circumference longer also. And I'll exaggerate, but when you warm up this ring then, and so hot, what happens is the circumference gets bigger as well as the width. And it's the circumference that makes the size of the inner hole. And so does the width of it increase? Yes. But also at the same time its circumference does. And so as I said, maybe a little bit of a surprise, thermal expansion means, because the circumference gets bigger, that the hole in a ring gets bigger when you warm it up. And that's a little bit tricky, I think, to see, and hopefully this helped. And of course, the other tricky thing, I think, to see, but maybe a little bit easier, is why then, when you take a material that is made out of two different metals, in this case, brass and steel, why does it curve when you warm it up and then go back to the same shape or straight when you cool it down? And then it would look something like this. If I start with a piece of brass on one side, a piece of steel on the other, and they start off at the same length, when you warm them up, they're both going to expand, but here's the key to this one. They don't expand by the same amount. Brass actually expands more than steel. So how does something get bigger, and they both get bigger, but yet one gets bigger than the other, and yet they still are hooked together because they are welded? And the answer is, that's what a curve is. The brass on the outside is actually a slightly longer distance than the steel on the inside. And so that's why they curve. They curve because of expansion. Do they both expand? Yes, but one expands more than the other. And so that's the key to this one. You got to realize when I'm talking about a thermal expansion, I am not saying all things expand the same amount. There is a difference from material to material. And then likewise, the other hard one is this one, why I wanted to show you is, remember the circumference expands, not just the width of it. So actually a hole gets bigger. It's why I brought a couple of things out here. No, maybe it's time we better take our break. Bummer, and I didn't get done with the chapter. So after the break, we'll come back and finish this chapter finally, and then you can do the homework on it. But here's kind of a fun one to see. Maybe you recognize this. Here is a thermostat here. And this is a thermostat, a little older one, so it might not be so easy to recognize. Maybe this one you would recognize, something you might have in your house or your apartment. And you use the dial to turn the heater on when it gets cold enough. And if you look at this one carefully, you will then see, maybe I should have left my heat on here. I'll go turn it back on. But I can control this, and this little coiled up metal piece is a bimetal strip that if I then go over here, and it's kind of warm in the room today, so I can't quite touch it, but when I touch it, that makes electrical contact, and that then turns on the furnace. So what happens when it gets hot in this room is this unwinds and pulls this back like that. And now you don't have electricity going to your furnace, and your furnace is not on. But if it gets cold in the house or the apartment, this then will contract. And eventually when it contracts enough, depending on how you adjusted it down here, it'll make electrical contact. So you decide, you the operator decide when you're going to make electrical contact and when the furnace will go on. And so like this one, I set right here, it makes contact at 80 degrees, and then anything lower than 80 degrees, it goes on. And so actually maybe this would be enough to actually see it alone here, is right now I have this coil making contact. And so you might say, okay, right now it's cold in the room. That's why it's making contact, so it can turn on the furnace. And if it warms up in the room, and so if I warm up that little piece of metal, you can see it pull back, and the thermal expansion breaks the contact and turns the furnace off. It's warm enough now. And so now over the next few minutes, maybe an hour, maybe even a couple of hours, it might cool down, and then it'll come back and make contact and turn the furnace back on. But as long as it is warmer than whatever I set it at, it breaks the contact and then doesn't then turn on the furnace. I'll show you another one here real quick, and we better break here, but you can see that same thing inside of an iron. Here's the bottom part of an old iron, but in that iron there is a little metal strip down here, a bimetal strip, and when it gets hot, so the electricity comes in and flows through here, making this plate hot. And as long as the two metal pieces are touching, the electricity flows. But when this thing gets up to a certain temperature, which I can control with a dial on the top, I can set this for low heat, medium heat, or high heat. And so if I set it for medium heat, let's say, it'll warm up till it gets to about that temperature. Then it'll get so warm that that bimetal strip bends and breaks contact, turns off the electricity. Not that I turned off the iron, not that I unplugged it, but the mechanics in here, the thermal expansion is being used. And so the engineers have designed it to say, okay, will this break contact at a certain temperature? And so that's what the medium heat is set up. Well, sadly, I didn't really give myself too much time to show you some of my favorite pictures, but if you're still hanging around here, let me go ahead and show you a couple, I'll only do 3 now, of some of my favorite pictures of thermal expansion, because thermal expansion, when it comes to engineering, shows up a lot. Here's one of them. If you've ever looked at a railroad track, you will notice that you put a railroad tie, and then a gap, and then another railroad tie, and then a gap, and then another railroad tie. Why is the gap there? Well, the gap is there because without it, the tracks don't have room to expand other than to expand in a kind of a curvy S shape here. And so these is a poorly installed railroad track because somebody foolishly put down the rail on a cold day and then put the second rail right up against it. And then the third one right up against it. And then winter left, summer came, and it got really hot, and then those railroad ties or those railroad rails had to expand, and they had to go somewhere, and so they made kind of an S shape here. Well, I'll show you another one real quick here, because another one of my favorite is this picture here. This is a picture of a pipeline. This happens to be the Alaskan pipeline. But this pipe goes a huge distance, something like 900 miles. And even though earlier on we saw the expansion of this brass rod and you said, oh, it wasn't very much, just like that railroad track, if it's not very much for 1 meter, can you imagine how much it would be after hundreds of meters or even hundreds of thousands of meters? I mean, 900 miles is a long distance. And so if you build a metal structure that is super, super long, like a pipeline, 900 miles, or a railroad track, which may be hundreds of miles, then even though it doesn't grow much per 1 meter, the total growth could be a lot, and you need room for that. And that's why those railroad tracks kind of curved. They needed that extra space, and that's what these are for. This is actually on a hot day, because on a hot day, these pipes got so hot, or they're also filled with hot oil, that they expanded, and they built them then to kind of crunch inward. If in a cold day, on a cold pitcher, these would expand out, and then it would come up and barely arch like this. And then when it's got hot oil in it, it comes in and does this little arching. And so the engineers know this challenge about thermal expansion, and they have to take advantage or engineer for the thermal expansion. And then one of my really all-time favorites, I wish I had more time to talk on this one, I'll just show you real quick. This is an airplane, a military airplane. It's an SR-71. If you're familiar with it, it flies something like 3.2 times the speed of sound. The surface of the airplane goes so quickly that they made it out of titanium. It's the only metal that wouldn't melt at the 2,000 degrees Fahrenheit that the surface is at. It's just incredibly, incredibly hot. And then the engineers realized a challenge. They're saying, ooh, how do we contain the fuel? How do we deal with this expansion? Because this airplane is 108 feet long when it's on the tarmac, and when it's in flight, it's 109 feet. It gets a whole foot bigger. And so the control rods that control the surfaces, how do you do that when the surfaces get further away depending on how fast it's flying? How do you account for all that? And so all of that was a challenge. But one of my favorite one is the fuel tank. Because the fuel tank, if you make it out of any other metal than titanium, it melts. Most airplanes make the fuel tank out of a rubber bladder. And so the fuel tanks are in the wings. And you fill up the rubber bladder, and the rubber bladder gets bigger and smaller, and of course the bladder is protected by the metal of the wings. You can't use a rubber bladder. And so here's what they decided to do. Here's their answer. They actually decided that when we build the plane, when it's 108 feet on the tarmac, what we'll do is we'll make it out of panels of metal, and we'll just put gaps in them, sort of like a railroad track. We'll just put little gaps. And so that way, when the plane goes flying and warms up, it'll expand and fill in those gaps. It won't buckle and twist. And that's how you're supposed to do a railroad track. So that's how we'll build our airplane. But it's kind of funny to imagine that if you walk up to this airplane, while it's on the tarmac, you'll see what looks like tiles and then gaps and then a tile and then a gap and a tile and a gap. There's like little gaps. And to make it worse, since you don't have a rubber bladder, if you put fuel in it, it would leak. It's not a completely enclosed container. But that's okay, as long as you can warm it up before all the fuel leaks out. And that's their answer. And they changed the fuel so it wasn't as volatile. But I like this picture because this is a picture right after the plane is taken off. Most of the fuel has leaked out. It hasn't warmed up yet. So you still got to warm it up, but it needs more fuel. So they do what they call mid-air refueling. So they give it enough fuel, even though it's leaking, it can take off, it can fly for a little bit, and then it flies to a tanker up in the air. And the person taking the picture is in the tanker. So imagine you and me, we're in the tanker, we're looking down. Here comes the airplane. The airplane right here, this opening is the fuel cap, if you will. And so we're going to lower down a boom, we're going to stick it right into here, and we're going to give this plane more fuel. But here's the best part. Right there, you see those strips, those black strips? That's fuel. These lines are the grid lines as the fuel is leaking out. It's not completely closed up, and you can actually see the fuel leaking out. Well, with that said, why don't I call it quits? I'm way over time here. Let's take our 20-minute break. I'll swap out some new equipment, and then I better wrap up. I told you it was a long chapter. Not a hard chapter, but I think it's a fun chapter. It's our first one out of mechanics. To me, it's a real fun chapter. A pretty straightforward chapter, but a long chapter. All right, I'll see you in 20.